Hey guys, so hopefully chapter 1 went okay for you. If it did not, I strongly encourage that you start asking more questions throughout these lectures, right? It's designed so that you yourself can be in charge of your own learning. So if you don't take responsibility for that, you're not going to do very well. All right, so 2.1, the start of chapter 2, is a review of functions and their graphs. So talking about things like what is a domain of a function, what's the range of a function, what is a function, things like that. Now, if you've been writing down these like headline bullet points here, you're wasting your time because if I've not said so already, because we'll get to each and every one of these things as we go through the lesson. But this is really just more review. Okay, so if you feel comfortable with domain and range, and you can plug in specific values into functions, and you know what the vertical line test is, and you can identify domain and range given like graphs and equations, then you should be good. And if not, then you can come back and look at the lesson when you've looked at the homework. All right, so let's move on. Now, these are some definitions that you may not need to know an explicit like word for word definition for, but you should be able to give it like you should be able to state the domain and state the range of a function, and you should know what a function is. So relation is the least used definition here. A relation is just a set of ordered pairs. That's all it is, just a set of ordered pairs. Then the domain in regards to a relation are all of the x values within the relation. So you've got a set of, so here's a relation right here. I'm skipping ahead a little bit, but I'll come back. So this is a relation, which is just a set of ordered pairs, right? This right here is the notation for a set, and these are called braces. So braces mark a set, and there are ordered pairs inside it, so this makes it a set of ordered pairs, making it a relation. Now the domain is the set of all x values of a relation. So that means this is part of the domain. Let me get my airbrush out. This is part of the domain, part of the domain, and part of the domain. All the x values in the relation. So your domain is going to be 1, 2, 3, and 4. So you've got this set, well, that is the worst brace I've ever done. 1, 2, 3, 4. All right, there. Oh, wow, this green is hard to see. I've forgotten about that. Don't worry, I got it. Sorry. All right, good. So that's the domain, the set of all x values of a relation. Now this definition is only in regards to a relation. We'll get to what it means for an actual function here in just a minute. And then the range, all the y values of a relation. So that would look like, you've got your 6, your 8, and your 9. So you won't list 6 twice, you just need it once. So your range is 6, 8, and 9. I'm not sure if you can hear my pen, but I hope not. Maybe you can turn it down because my microphone is very, very sensitive. So, a function is a relation in which every x value only has one y value. So, every x value only has one y value. So, this means that if you were to look at 1, the x value, it can only have this one y value, 6. Now 2 could only have one y value, in this case 6. That's okay. They both have 6, but it's not like x values, like y values can be used multiple times, but x values cannot go to multiple y values. All right, I know that's kind of confusing, but it's easier when you can actually test for it. Basically, if you see the same x mapping to multiple y's, you've got a problem. It's not a function. Here 3 goes to 8, and here 4 goes to 9. These are all okay. They're not, multiple x's are not even present here, so we don't have to worry about this being an issue. So this is a function. So given this relation, what is the domain and range? Well, look at that. We've already got the domain and range. Is the relation a function? And yes, it is a function. And that is because each x value only maps to one y value. I'll give you an example where, here, if this set also had this ordered pair, it would not be a function, because if you see 3 maps to 8, and then here 3 maps to 2, that's not allowed. Your single x value can only map to one y value, right? So, moving on. You guys should try. State the domain and range of the relation. State whether state whether it is a function or not. All right. So looking at this set of ordered pairs, state the domain, state the range, and tell me whether it's a function. All right. Go. Well, your domain are all your x values. So 6, 8, and 9. And your range are all the y values. 1, 2, 3, and 4. Oh, that's not the right thing to do. And man, these braces are just the worst. I just I can't see underneath my own pen, and so it's hard to do. All right, so then state whether it is a function or not. Well, here you look at all of your x's and see if there's multiple x's. 6 and 6. So if they map to different y's, we got a problem. 1 and 2. So this is not a function. Not a function, because you have one x mapping to two y's. 6 is mapping to 1 and 2. That's a problem. All right. Now, remember we were talking about one x value mapping to more than one y value, right? So quickly, I'm going to skip part of this slide here and show you what that means. So see where my pen is at over here? Look at the x value 1, right? Where that touches on our graph. Well, it would touch here and here and here. That means these ordered pairs, like approximately 1, -3, 1, 3.7-ish, and 1, 4, 5, 6.2. Notice how if this was written out as a relation, then we would have the same x value mapping to multiple y values. All right, do you see this? This is what creates the vertical line test to check if something is a function. If a vertical line drawn through a graph touches the graph at more than one point, it is not a function. So if you look here, if I were to draw a vertical line, it touches the graph here, here, and here. That means that this graph here is not a function. Whatever this equation is, it's not a function. So this vertical line test is very handy. And this is something you should see visually. Like, this is something you should see with your eyes, and you should imagine the vertical lines. So, and this doesn't mean like a single vertical line. This means any possible vertical line drawn on the graph. So over here, over here, over here, over here, any of these vertical lines, if they touch the graph, any and every vertical line, if they touch the graph at more than one point, it is not a function. This is like you should try to prove by counterexample, like give me a vertical line where it does cross at more than one point. That's the easiest way to do it. So here you look, oh, I can make one right here, and it crosses at more than one point, right? But on this parabola, it's going to continue to go up and to the left and up and to the right. It's never going to go straight up. So if it's constantly going left and constantly going right and never overlapping on itself, there's never going to be a vertical line that touches at more than one point. So this is a function. This one right here is a function. Now this next one, it's got this loop business going on, but it's still going to be a function because it never like overlaps on top of itself. So you can keep drawing these vertical lines and it still touches the graph just at one point. So it touches here, 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 and so on, right? So this is all okay. Still passes the vertical line test, which means this is also a function. And then we've already talked about this one. It is not a function because it fails the vertical line test. This vertical line touches the graph at 3 points, and that is bad. All right, moving on. Next, we're switching gears a little bit. We're going to evaluate functions at given values. Just plug in the given value for x or whatever your variable is. So this is called function notation. This is f of x, f of x. And that means the function is called f, and the variable or independent variable is x within the function. So this says find f of 2, which means you replace x. Notice how there's this replacement going on. It used to be called x, and now it is 2. So anywhere where you see an x, you will put 2. That's all you do here. All right, it's just simple substitution. So f of 2 is equal to where all of the x's have been replaced with 2's. 2 squared plus 3 times 2 plus 5. And that equals 4 plus 6 plus 5, which is 15. Okay, that's all we're doing here. Now, remember, this is like a substitution. Regardless of whatever, I'm saying this specifically to try to avoid confusion coming up here in just a couple minutes. Whatever is in here, you will just substitute it into the variable. That's it. It's just a direct substitution. Whether it's a 2, or whether it was a 5, or whether it was a y, you would just substitute it in. Just exchange the x's with the whatever it is. So, it's just a direct substitution, all right? We've got f of x plus 2 this time. So instead of writing just x, we substitute x plus 2 in. So f of x plus 2 is equal to x plus 2 squared plus 3 times x plus 2 plus 5. Notice, anywhere I see an x, I write x plus 2 in parentheses. Right? It's just a direct substitution. All of the rest of the equation is still there. We've still got our squared, right? We still got our squared. We still got our plus sign. We still got our 3. And we still got our plus 5. It's just all the x's have been replaced. Okay? And then you go ahead and simplify this. So you've got x plus 2 quantity squared is this. X plus 2 times x plus 2. And you'll have to FOIL this. Plus, and then here you distribute. And here you've got plus 5. All right, so this FOILs out to be x squared plus 4x plus 4. And I just combine those into 11. And then here we've got x squared plus 7x plus 15. This is just combining like terms. I combined the 4x and the 3x to make 7x, the 4 and the 11 to make 15. And then the x squared doesn't combine with anything. And in case you've forgotten, like terms with variables, you can't combine variables unless they have the same exponent tied to them. Okay, so x squareds cannot combine with regular x's. Not allowed. Illegal maneuver. 10-yard penalty. So here we've got f of negative x. And I want you to try this and simplify it. Again, it's a direct substitution. All right, let's see if you were right. Or, you probably didn't even pause the video. What am I talking about? You don't pause these videos. Unless you do, and then good job. So, negative x times negative x is a positive x squared. And then your 3 times a negative x is a negative 3x. And that can't simplify anymore. This is a plus sign. I know it doesn't look like it, but it is. All right. Find the domain and range of a function's graph. Now, this is the next part. Let me see how much more we have to cover. All right, we should be pretty good. This should be done in like 5 or so minutes. So, not a very long lesson. Find the domain and range of a function's graph. So what I want you to think about, if you're, really rusty in math, is think about all of the ordered pairs that fall on the graph. All right? Imagine all of these ordered pairs. Every ordered pair imaginable. Infinitely close together, right? We're talking like if we had this ordered pair and this ordered pair, there is an infinite number of ordered pairs in between here. The more you zoom in, you can still find ordered pairs in between here. But imagine that this graph is made up entirely of ordered pairs that are so close together you can't see in between them, all right? And then imagine that all of those ordered pairs were written out. This is the foundation of the logic to deal with finding domain and range. It's still a set. Man, I am so bad at these today. It's still a set, and let me write D. And it's a set of x values. And if you were writing this graph out, like I was explaining, where all the ordered pairs that lay on the graph, right, we would have to see all of the x values and put them here. That is what this domain would be. But there's a problem, because you could continue to zoom in and continue to zoom in and find more and more ordered pairs that fit in this relation, right? So here's the idea on a graph. Here's how you want to think about domain. You want to think about all of the x values. This is only for domain. All of the x values that exist. So we've got all of the negative x values, like -1, -1.5, -2, -3, -10, right? And you want to see if that x value, somewhere along the x value, touches your graph somewhere. If it does, then that number is part of your domain. If it does not, then that number is not part of your domain. So based on where the graph is curved and shaped and where it's pointing towards, this is where you'll have to imagine. You have to think that our graph continues to go up and to the right and continues to go up and to the left forever, all right? Try to picture that. And then try to think of x values where it does not touch the graph. That's the next step. So here you've got this x value, this x value, this x value, this x value, this x value. Every one of these x values touches the graph somewhere. Touches the graph, and it will, if you can imagine, infinitely to the right, because the graph continues to go right. There's always going to be some point, like at 100 over, where it's way up there. Right? I'd be making large hand motions to gesture, way over there. So regardless of where you draw your vertical line, this graph will cross it at some given point. That means that every x value is on your graph. So like this is like -4, 0. This is like -8, 4. Or that's 5. Wait, 1, 2, 3. No, it's 4, right? And then this would be like -11, or -13, whatever, 8. And you can keep going, right? You can keep going, -20, +15, +20, whatever. So all these x values are part of your domain. Okay, hopefully I'm not like beating the dead horse here. Hopefully you're still understanding what's going on. So since every x value that you can possibly think of will be represented on this graph, the domain is going to be all real numbers. All real numbers, right? And another way to write that is something called a double R. And it looks like this. It's an R with 2 strokes. Right, just like that. This means all real numbers. Now, your range. Let's talk about range next. It's the same exact concept, except with y values. So if you're looking at range, you're trying to think of every y value and think about if it is touching your x, or not your x, if it's touching your graph at some point. So at 0, it's touching. At 1, it's touching. It's touching here and here. At 2, it's touching here and here. At 3, it's touching here and here, and so on. 4, it'll touch. 5, it'll touch. 6, it'll touch. So looking at positive numbers, it looks like it's going to touch your graph everywhere, even in between all these, right? Because it's a consistent, continuous graph. However, moving down, look, if I draw a line here, it's never going to touch my graph, ever. That means this y value is not part of our range. It's excluded. As a matter of fact, every y value below the vertex here, the bottom of the V, is not going to be in our domain. So all of these negative horizontal lines are not in your range. Excuse me, if I said domain earlier, I meant range. All of these y values are not in your range, which means only the y values that are equal to 0 or greater than 0 are part of your range. So that means the y's that are bigger or equal to 0 are part of your range. Simple as that. Okay, last example. Find the domain and range of the function's graph. So here, if you think you understand the concept, go ahead and do it. and then I'll walk you through it. Hopefully, if you really already understand domain and range, you've skipped this. And if you're still struggling, then please try to think about this. Try to think about what x values would work or would touch the graph and what x values wouldn't, and then think about what y values would touch the graph and what y values would not. Try to think about that and see if you get it right. So, hopefully you came to the conclusion that this was the x value that was farthest to the left that was still on my graph. Because every other x value to the left of that one is not going to cross this parabola, because the parabola only goes to the right. It doesn't go to the left any more than this. So that means all of these values are never going to get crossed by your graph. So that means -1, 2, 3, 4, 5. -5 is the farthest to the left x value. And then all of these x values are going to get touched at some point. So all of the x's that are greater than or equal to -5, those are your values for your domain. Then your range is all of the y values, just all of them. So all real numbers. And the reason for this is because the simplest thing to think about is the graph goes up forever and down forever. It's as simple as that. There's no gaps. The graph goes, this is continuing in an upward trend and this is continuing in a downward trend. It doesn't quite look like it, but look, it is making downward progress and it'll continue to do so. So since the graph goes down forever and the graph goes up forever and there's no gaps in the middle, that means every y value is going to eventually get crossed, since it is going down and it's always going up. All right, that's another way to think about it. If it's going up forever and down forever and no gaps, then the range is all real numbers. All right? So if you have any questions over that, or you get to an example in the homework and you have questions, please let me know. All right? These videos are not going to do you any good if you don't try to learn from them. All right? Imagine that this was just me lecturing on the board. All right? There's your homework. Do your homework, turn it in on the assigned due date, and ask questions if you need help. All right? You should be able to find the homework assignment on my website. All right. See you guys.